So we're going to talk a little bit about inequalities. So basically, a common thing to do when doing math or computer science is to do strings of equalities. And so it turns out that also strings of inequalities are also very useful. And I'm going to just talk about a little bit about that for this class. Okay, so first off, we're going to recall the definition of less than or equal to. We're kind of taking less than to be this atomic thing. We know how to evaluate whether or not two things are less than each other, and we more or less know that when things are equal to each other. So in general, for real numbers, every number is either equal, less than, or greater than. And so we're going to also say that a is greater than or equal to b. That is going to mean that either a is strictly greater than b, or a is exactly equal to b. Okay, so when we do work, a lot of times it's very convenient to break things up into individual steps. And so when you break things up into individual steps, for instance, one thing that you might want to do is you want to show that two things are equal. So when you want to show that two things are equal, the way that you do that is you show that there is some chain of intermediate equivalences, and altogether that means that your two final things are equivalent. This is at least one possible way you could do it. So for instance, in this case, if you have that both a is equal to b and b is equal to c, well, we know that since b is equal to c, every property that b has is also shared by c. So in particular, one property of b is that b is equal to a. So that means that c also shares that property, and so a is equal to c. And that's equality elimination. So what that allows you to do is it allows you to take strings of equalities like this, where a is equal to b, which is equal to c, which is equal to d. All you have to do is justify the individual lines that 1, a is equal to b, 2, b is equal to c, and 3, c is equal to d. If you can justify those three individual lines, then you can conclude that since a is equal to b and b is equal to c, then a is equal to c, and then since a is equal to c and c is equal to d, we get that a is equal to d. So those intermediate parts are like so common that we don't actually really think about them when we're doing this kind of reasoning. But it is what's happening in the back of our heads. We just are going to kind of be skimming over that because it's a very common pattern, and we don't want to have to elaborate like that level of detail every single time. Okay, so this is a relationship that's basically what's called transitivity. It's if a is related to b and then b is related to c, if that makes a also related to c for any triples a, b, and c, we call that property transitivity. It turns out that less than also enjoys the property of transitivity, that if a is less than b and b is less than c, then a is less than c. So an example of this might be something like 1 is less than 4 and 4 is less than 13, therefore 1 is less than 13. For the purposes of this class, we're going to just take this as axiomatically true. We're not going to really question why this is true. We're just going to take it as true. Okay, so here's two examples of relationships between a and b, and then a relationship between b and c, and then we are going to try and conclude a relationship between a and c. In general, you can't always conclude a relationship between a and c. For example, if a is less than b and b is greater than c, there's not really any relationship you can conclude between a and c. For an example of this, if a is 0 and b is a billion and c is 1, then c is actually bigger than a. But if b stays a billion and then a and c switch, so that c is 0 and 1 is a is 1, then a is bigger than c. Or we could set a and c both equal to 0 and b equal to a billion, and this is still true. So if the signs switch directions, then you can't really conclude anything. And so in general, we have the same kind of results that if you switch your directions, you can't really conclude anything. So you want to make sure that your inequalities are always going in the same direction. Okay, so some other examples of ways that we can mix things. We could have maybe a is less than b, and that b is less than equal to that b is equal to c. It's easy to see here again that just equals elimination. The b turns into a c, and you get that a is less than c. Cool. How could we use something like this? Well, we might have that like a is equal to b, and then we have that that's less than c, and that turns out to be equal to d. Altogether, we're kind of skipping an extra hidden lemma here, which is that a equals b less than c means that a is less than c, and then a less than c and c equal to d gives you that a is less than d. But you can easily show this all, it's just equality elimination a bunch of times. Since c is equal to d and b is less than c, we get that b is less than d. And since b is less than d and a is equal to b, we get that a is less than d. And again, equality elimination is just so common that we just kind of skip it and think of it as a normal thing that we just do in the back of our heads. Okay, so we showed how strict inequalities mix with equalities. We looked at strict equalities with themselves. We'll mix strict equalities with non-strict inequalities now. Okay, so if a is less than b and b is less than or equal to c, so this is where our definition of less than or equal to actually matters. We know then that either b is equal to c or b is strictly less than c. In the first case, if b is equal to c, well, we can just use equals elimination. We know that a is less than b, so a is less than c. Cool, that's what we're trying to prove. That case is done. Case 2 is that b is strictly less than c. We also know that a is less than b, so we get this chain of inequalities. And we know that when we have chains of strict inequalities, we can just take that as the endpoints, and that tells us that a is less than c. So in this case, we get a is less than c. We get a is less than c in either case, so a is less than c is just true. So whenever a is less than b is less than or equal to c, a is less than c. You can sort of think of this as taking like the strongest claim out of the three. There are three possible claims. The three are equality, less than or equal to, and then less than. And we always are taking the strongest one. So less than, like, that's saying that there is a gap between a and b, and then b less than or equal to c means there might be a gap, but c is definitely not smaller. So given that there is a gap somewhere, though, we know that the gap has to persist to the very end. Okay, so last example here, if a is less than or equal to b and b is less than or equal to c, then a is less than or equal to c. So we might notice here that when we have the option of equality throughout, then it has to stay throughout at the very end. Here, there was guaranteed to be a gap, so there has to be a gap at the end. We could have actually said less than or equal to c, because if a is less than c, then certainly a is less than or equal to c. Okay, so final example here. So we're going to assume that a is less than or equal to b, and b is less than or equal to c. Let's take this first one and expand what it means to be less than or equal to. Either a is equal to b, or a is less than b. So first case, a is equal to b. We know b is less than or equal to c, and that a is equal to b. So together, eliminate that b, turn it into an a. We get that a is less than or equal to c. Okay, that's what we're trying to prove, so that case is done. The second case is that if a is less than b, then we know that both a is less than b and b is less than or equal to c. If we look back up here, we might actually recognize that as something that we've already looked at. And in this case, we know that a is less than c. So we get that a is less than c down here. It's the exact same reasoning. And so we said earlier, if A is less than C, then certainly A is less than or equal to C. That's basically just like disjunction introduction. We know that one thing is true, so at least one of the two cases is true. So in either case, A is less than or equal to C. So long story short, these kinds of chains of reasoning are common. They're very convenient. We're kind of going to shuffle off the details because they're fairly tedious and we don't want to get into them every single time. We're going to upload a drill at some point to practice them in more detail.